the service providers got very interested and have stuck with it this time, and are even with the price of oil and gas returning to higher levels, they've really stayed the course and maintained their interest. And there's been a lot of new developments in geothermal. There's been a lot of interesting news. There's several different alternatives now to geothermal energy, besides just the traditional hydrothermal, and we'll talk about that a little bit. Here at what the company I'm working for, we're starting a new company called Mazama Energy. We're very new. We're less than 12 months old. It is an outpouring from work done by Rock Energy. Rock Energy started in 2007 in the enhanced geothermal space. And we took the learnings from that, and our goal is to develop a new company whose objective is really to make geothermal competitive with the price of gas. We want to see the price, the number of megawatts per wellhead driven up, get the energy density up, in order to make it competitive without significant government influences and government subsidies and feed-in tariffs. We think that if we can get the energy density up, we can make it really scalable worldwide. The goal being that in order for it to sustain itself, this is what we've seen work for oil, for wind and solar, get off the ground, and now they're competing on their own. We do think geothermal can do that. Geothermal's sort of been the unwanted stepchild of renewable energy for a long time, partly because it's been around for so long, and everyone thinks it's sort of a mature industry, a mature energy development technology. There's a lot to learn, a lot to do, a lot to change, and that's what that's our objective at Mazama. Now let's talk about what is SuperHot Rock. What we're talking about here is higher energy density. So getting down to temperatures where the state of water reaches a supercritical state, which is not liquid, not gas, somewhere in between. Something with a very low viscosity, a very high penetration, yet a high energy density energy load. It can carry a high heat capacity. So this is just a graph of pressure versus enthalpy as a function of temperature, the different equations of state. This is where conventional geothermal steam plants operate in these enthalpy ranges with these pressures. This is where these are conventional binary turbine plants where they operate. We're talking about trying to get plants and fields that operate up in this realm. So higher enthalpies, higher pressures, higher temperatures. We believe that if we can get wellheads that are producing fluids in this range, we can produce a fluid that's much more economically viable. We can produce a lot more money for our generators. The question is, why do we want to do this? The value proposition is that we produce more energy with less infrastructure. So not only do these fluids carry more water at 400, 450 degrees Celsius, as opposed to 200 degrees Celsius, we need less infrastructure at the surface. You need a smaller energy plant per megawatt. So if we can double the temperatures of fluids being produced at the wellhead, we need less than half the size of a power plant. And reducing that amount of infrastructure, that amount of steel required at the surface to produce energy, reduces our costs tremendously. It reduces not just CapEx, but also your operating costs. You've got less material you need to operate, less maintenance, less personnel per megawatt. So everything sort of works out. When we look at the fields across the world, when you look at the megawatts per well as a function of reservoir temperature, this is a very generalized approach, but sort of it's a broad brush look at geothermal plants across the world and across time. Traditional power plants, conventional power plants operate in this range, 200 to 250 degrees C at the high end. This is like the geysers in Northern California or the Salton Sea or Indonesia or New Zealand. If you look at areas such as the middle of I'm going to be focused on the United States, but this is the Nevada plants. These are binary plants. These are the ORMAT plants, the plants that are being built in the Nevada area, Reno, Utah. Some of the plants in Germany and France and the speculated plants in Switzerland are also operating in this range. So these are economic, but only in specific cases, and it's tough to make these work in an enhanced geothermal type environment. And I'll talk about that in a little bit, why it's so expensive. Looking at the white space that we're trying to move into is up here beyond 350 and 400 degrees C, where we can get megawatts per well in the range of anywhere between 20 and 40 to 50 megawatts per well. Our future plans talk about where our initial plants that we're targeting are in this range. This is our pilot plant that our objective that we're looking at now. I'll talk about that in a little bit, but we're looking at if we can get upwards of 15 megawatts per well. This is like some of the highest producing geothermal wells currently in the world. We think this can be a low-end type plant in a super hot rock situation. If we move up as our technologies mature between 10 and 20 years, we're hoping to have plants that produce megawatts per well in the range of 35 to 50 megawatts. And the market for this is tremendous. Where do we reach these temperatures, these 400 to 450 degrees C temperatures? Using current drilling technologies, we can reach these conditions, approximately reach 50% of the world's energy market, or within drilling ranges using conventional technologies. So in the up to 9 to 10 kilometers depth range. There are technologies out there that are being developed, hoping to extend drilling technologies beyond 10 kilometers down to 15 or 20 kilometers. In those situations, we would be able to reach pretty much 90 to 95% of the world's global energy market using those drilling technologies. But just today, using today's conventional technologies, with a little bit of tweaking and a little maturing and being sensitive to the technologies and how they're handled, we believe we can get down to 10 kilometers and reach 50% of the world's global market. Now, we're using the term super hot rock. And 10 years ago, 15 years ago, people were talking about supercritical geothermal. In Iceland and in New Zealand, they talk about reaching supercritical reservoirs. So drilling into naturally occurring supercritical conditions. We're not focusing on supercritical conditions per se. We use the term super hot to indicate it's much hotter than what conventional resources are, but we're not so temperature dependent. It's really pressure, it's not so pressure dependent, but temperature dependent. So this graph here represents the range where supercritical fluids occur in natural environments. So high temperatures, high pressures. This is like the international deep drilling, the Iceland Deep Drilling Project #2 in Iceland. This is like the Kafka project. This is like the Descramble project in Italy. These are realms where the fluids occur in high temperature, high pressure conditions. These fluids are very corrosive, naturally occurring fluids. Our focus is temperature based because that is really the benefit. That gets us the energy density that we need per wellhead. And so these are conventional systems here represented by these large dots. The circles are of course representative of the size of the field. The center of the dot being the temperature and pressure realm for each field. We want to push this type of field development out into this range, above 350, 375 degrees C. So this is like the Iceland Deep Drilling Project 1. This is Venel in Italy. This is the Prati well. These are conditions where we've reached these conditions in the past. Approximately 20 to 25 different wells have reached these conditions. We believe that pressure is not so dependent because it's the temperature we want to get to the surface that carries the enthalpy that we're desiring to get the economics that we need to make these wellheads competitive. So moving the field of development from this range to this range is what we're after. So higher temperature gradients. So these shows you the temperature gradients where these different fields occur at. We're talking about the Newberry field in Oregon. The Newberry field occurs right about here, so it's really on the cusp of getting into higher pressures. But again, pressure is not super critical for what we're after. What we are after is permeability. So why EGS? So I've used the term EGS a little bit. Let me back up and explain what enhanced geothermal systems refer to. And this is essentially creating permeability where there is none. So in having a traditional hydrothermal system, you have to have three things. You have to have heat, you have to have permeability, and you have to have accessibility. It has to be at the right depth. If we take away the permeability requirement, if we can target fields where temperature is just accessible to conventional drilling, we want to create the permeability and make it. So essentially, it's hydrofracking. We call it hydraulic stimulation because hydraulic fracturing has received some bad press in the last 30 years. So we're talking about hydraulic stimulation, creating permeability where there is none, taking away the risk that there isn't going to be permeability at these reservoirs. And another reason we are focusing on EGS at Mazama Energy is that getting down to the depths where super hot rock conditions occur, and that is really above or below a depth of 3 kilometers, permeability really drops off. Naturally occurring permeability really drops off at those depths. Crusts tend to be not deformed enough, not disturbed enough at these near ductile conditions that you have to create your own permeability. And what we've shown here in this graph is areas where these are situations or fields where permeability was induced using EGS technologies and created fields where they went from what was considered a non-disturbed crust to a disturbed crust. And you can see the disturbed crust. These are all projects out here that have proven to be economically feasible. So this is where the geysers, these are naturally occurring systems with naturally occurring permeability. This is economic. This is COSO in Central California. This is economic. Krafla, Neal Hot Springs in Oregon. These are systems where there's enough permeability to make them economic. This is the Newberry EGS demonstration project that ran from 2010 to 2017. We worked to improve permeability there. We never did get enough permeability to make the field economically viable. So this is a situation where I'll talk about this in a little bit. We want to take this permeability and carry it into the disturbed crust domain to make it economic. This is the Fervo project, which is recently published in north central Nevada, where they took two wells, combined them, took a crustal environment that was considered undisturbed, and using stimulation, an EGS in a greenfield, carried it into what is now basically considered an economic project. They're producing hot water economically. They're adding it to the plant, and we haven't seen the published results from that yet, but that hot water is going into the plant and is producing electricity from what is considered a greenfield type environment. So there are different types of engineered systems for heat extraction. There's the closed loop system. This is the EVER type system with multi-fingered, lots of drilling, not much risk in terms of the geologic environment. So this is very geologically independent, this type of system, because all the drilling is closed loop. It does require a tremendous amount of drilling. It needs a lot of drilling length in order to get the surface area needed to be a viable resource, producing resource. This is the model of what we call hydroshear stimulation. This is a model that Altarock worked with for many years, and this is what is also considered traditional EGS. This is stimulating existing fractures in the rock, not trying to actually induce fracture, not creating tensile failure, but creating permeability in existing fractures. This we found to be very difficult to produce. To get enough surface area to be economic was very difficult. It's also difficult to predict. There's so many variables in the subsurface. This turned out to be geologically risky in terms of trying to characterize what kinds of fracture network you can develop and try to predict fluid flow. Let's skip over here to this is the planar fracture model. This was also a traditional model. This was carried forth by a lot of oil and gas technologists. The idea that we could create penny fracs to connect two existing wells, going heel to toe and toe to heel, trying to connect two wells. This also turns out to be much more difficult than the models predicted. The variability in fracture permeation and permutation through the reservoir is hard to predict. And so connecting two wells that are pre-drilled turned out to be very difficult. The Fervo model is a modification of this, where they drilled one well, created the fractures, and then drilled into it. And that is the model here that we're going to be using in Mazama. This is what we call a hybrid fracture network. We use the term, we call it thermal lattice. This is a combination of your hydrofracture model and your natural fracture permeability stimulation model. So we're going to be creating artificial fractures, creating hydraulic fractures through stimulation, and then stimulate after that with low pressure to activate existing fractures that have been encountered by your penny fracs. So the objective here is it's a two-step approach that will give us the large amount of surface area we need with the minimum amount of drilling and really trying to optimize fracture creation in subsurface. And so this is what we're after in our demonstration project that we're going to be proposing to the Department of Energy and carrying forward as part of our business model at Mazama Energy. We think, now there's many different models and many different cases, and different folks will argue different situations. This is the model that we're arguing is best suited for SuperHot Rock reservoir development. So let's skip over to field work. I'm going to talk about the Newberry EGS project. This is in central western Oregon, between the towns of Bend, Oregon, and Lapine, Oregon. This is a large caldera system. Newberry is a shallow sloped, large volcano. It's basically the biggest volcano that people in North America have not heard of. It is on scale with, it's about half the size of Yellowstone. It is a large caldera system, large magnetic body at shallow depths. It's quite accessible to drilling. People have looked at doing traditional hydrothermal, geothermal there for several decades, since the 80s, unsuccessfully. In 2008, 2 wells were drilled there on the west flank in searching for a hydrothermal system, which turned out to be unsuccessful. And they came back, they discovered this very impermeable rock. And so Altarock came along in 2010, bought up the leases, and proposed a demonstration project to do traditional, what we call traditional hydrothermal stimulation, hydroshearing stimulation. That is low pressure stimulation, that is below SH min, the maximum horizontal shear stress, trying to activate activate existing fractures in order to create a reservoir that we can flow water into and create a heat exchanger. This is a timeline of the work that's been done there since 2008. We had 2 stimulation projects. These were projects that were funded through the Department of Energy, developing really the techniques for doing EGS. So getting in the field, understanding how to do microseismic system installation, how to do monitoring of fractures as they occur, as we do stimulation, following it in real time, the progress of fracture stimulation across the reservoir. We proposed to be on the Forge, one of the site for Forge. We were one of the finalists. Utah was ultimately selected. Probably was the right decision considering the success that they've had at Forge. I think they've done very well and demonstrated that's a very good site for what they're doing. We had an international continental drilling project workshop there in 2017. We proposed the site for deeper drilling, going after the deeper resources. We had some success and some traction there. We had a lot of interest. Ultimately, funding was not successful in being raised, and we shut the project down in 2018 when it went dormant. And that was until really in 2020 when interest came back into geothermal from the oil and gas programs, looking at the fact that the price of oil and gas had gotten so low. Everyone turned in the United States, everyone in Houston turned towards the possibility of doing geothermal drilling and geothermal resource development. We've got renewed interest, and so we renewed the project. We've got some funding to carry some ideas forward, and now we're proposing to do a SuperHot Rock EGS technology development and demonstration project there. We're hoping to hear from the Department of Energy within, it's already 6 months delayed in their announcement of those demonstration projects. We're hoping to hear from them by the end of the year. In summary of what we did there, this is a map of the microseismic array that we installed in order to monitor the project. It was really considered at the time sort of state of the art in terms of microseismic arrays and microseismic monitoring. It was sort of the gold standard up until a few years ago, and now with the advent of digital fiber and digital fiber acoustic sensoring, acoustic monitoring, the technology is really being carried forward. And there's a new understanding of the importance of microseismic analysis. Our approach was going into that project was large volumes, low pressure, long duration stimulation. And we went to Baker Hughes and had them develop a couple of specialized pumps for us that allowed very high injections at relatively low pressure, so 3,000 PSI over periods of weeks to months. So these are pumps that will operate. These are centrifugal pumps laid on their side that have long-term duration with low maintenance. Ultimately, we found that it was really not necessary. We found that primarily most of our stimulation and natural occurring fractures occurred within the first week to 2 weeks. So having these long duration pumps we sort of learned that this wasn't necessary to have this kind of technology, that doing low pressure stimulation over long periods of time is not necessarily the best objective. But we did have success in creating reservoirs. These are this is one map or one graph of our seismic events that were mapped during the time. This is in 2014. We had kind of a 2-phase stimulation campaign in that project. We were able to map out this is a voxel array model showing where our fractures occurred. This was used in plotting our second well. So the existing well, which is called 5529, was our treatment well. We created a fracture network we plotted and just designed a well we called 55A29, which was going to be our production well. Ultimately, that well was not funded and not built, but we took it as far as doing a full well design, actually permitted the well. The ultimate goal, the output of this project was we were able to map the fractures. We were able to create moment tensors that allowed analysis of the deep-seated stress regime. We did not have information from very deep because no one had visualized down there. And being that it's a volcanic environment, the stress regime changes quite radically as you go through depth. We were able to map that out. We were successful in doing our seismic analysis and doing our MEQ location, our micro earthquake location. We ultimately did not create enough reservoir or enough surface area really to be economic. And that's one of the reasons that the second well was not funded, is that doing a hard analysis of what we could have produced from this doublet, our funders determined that, well, it really wasn't going to be competitive. And the ultimate goal for this project is to be an economic site, not just a research and development site. And we just didn't develop enough surface area at depth to create enough flow to support any kind of power plant at the surface and get any kind of power economically feasible power on the grid. And so that's one of the reasons that the project was put into quiescence. And so from that work, we had lots of remaining questions on how would we carry it forward? What would it take to make the project economic? We needed better conductivity, better productivity. We didn't have, without a production well, we didn't have a well to frack into. We found that was quite important. We essentially felt like we were inflating a balloon, and that balloon we can't maintain constant pressure. And while the reservoir would grow, but without a second well to connect into, we ultimately didn't get flow through a reservoir. We didn't get the connectivity of the flow and the increase in permeability that comes with creating that flow that we've modeled for enhanced geothermal systems. And so economic generation at 250 degrees C wasn't compelling. Going into 2017, looking at the idea of doing SuperHot Rock, that's when we sort of pivoted towards higher temperature conditions. We've modeled that. We think we can get the price of power down at our nth plant development down in the range of $45 US per megawatt hour, which is about almost half of what it is now at 200, if you're doing EGS project at 250 degrees Celsius. We think we can get the power with the smaller power plants at the surface, the less number of wells, the less amount of infrastructure, fewer casings, less cement. We believe we can reduce the price of power by half. That will take several steps through demonstration projects, and it'll take several iterations and generations to get to that point. But we think with what we've modeled based on what we've done, looking at the hybrid approach, the two-phase stimulation approach, doing tensile failure first, followed with hydrosharing, we think we can get the complexity and the amount of flow that we can maximize the reservoir area per well. So what have we learned? What have we learned about EGS SuperHot Rock work in the past, and how we carry that forward into our ambitious projects, our ambitious plans for the future? These are some of the wells that have drilled down into SuperHot Rock conditions in the last 15 to 20 years. Almost all of these projects have hit these conditions. Most of them were intentional, not all of them. In most cases, these wells have all been made dormant because there's been difficulty in handling the fluids. So we know we can get to these conditions. We know we can get down above 400 degrees C. The question is, what do we do when we get there? The lessons learned from these projects include how to drill to 500, even as high as 500 degrees C with different cooling techniques, different material handling techniques, different cementing techniques. We know we can hit permeability of those depths. We've looked a little bit at creating permeability in open hole stimulations. In Iceland, the Icelanders have determined how you can turn the corner at high temperatures if you have the right instrumentation, the right cooling. The descramble well in Italy showed that you can actually get through areas with no returns and still successfully complete a well. But there have been failures, and there's been some stumbling blocks along the way, which of course, anyone who has had a failure, that's where you learn the most, is from your mistakes. Near surface corrosion, material compatibility is a big one. Naturally occurring supercritical fluids are highly corrosive. They typically carry high loads of sulfuric and hydrochloric acid. They tend to eat through, and they have a very low pH. They tend to eat through most steels, unless you've got a very resistant steel, or let's say you use titanium. Most of the projects in the past are sort of on shoestring budgets, couldn't afford titanium. This picture on the right, this is the IDDP1 well. It flowed for a while very successfully, eventually corroded through the low carbon steels they were using at the wellhead, and they lost their entire wellhead structure. One of the biggest lessons learned in drilling these deep wells is don't stop your drilling. And if you pause while drilling, the heat up can be detrimental to your entire program. And what's more is if you do stop and you do slow down and things things heat up, you need to really back out and start all over again with your cooling program. That trying to re-enter a hot well too soon can cause total failure. Cementing, sorry, one of the things I skipped over a little bit was cementing is extremely difficult at these temperatures. There's been a lot of new development in cementing technologies in the last 5 to 10 years, which are very encouraging. We've seen some very good cement work being done, looking at the actual chemistry of cement at these higher temperatures. Retardation, the retardation programs are important and need to be really well thought out in order to make sure your cements don't set up too quickly or don't cool off, that they stay liquid long enough, but that they don't stay liquid too long. So what is the state of the art of the technology that we've learned from traditional projects? One of those is that we can get to these temperatures. The well completions are very challenging. Experience tells us that we need really, really good planning. We need to really think these through very thoroughly before entering the field at all. We can't really do anything on the fly. You need a really robust risk assessment and mitigation programs. The wells that have been successfully installed really took their time getting there, walked through all the steps, all the phases, and all the mitigations, really having 2 or 3 mitigation steps for every risk that you can identify before going in the field is pretty much a standard. You have to have that. EGS and low permeability conditions hasn't been attempted. Tensile failure stimulation, fracking in these kind of conditions hasn't really happened. We don't have any good examples in the field of anyone fracking rocks at these kind of almost ductile conditions. So we're approaching the ductile transition in the rock regime. We don't really know. We have models of how these rocks will behave, but we don't really have good field data to back that up. We don't know how these fractures are going to permeate through the reservoir. We have very little idea what the fracture toughness is going to be when we do fracking. So having field data is actually key, and that's one of the big goals for Mazama, is to go out and get some field data and understand how our models are performing in relationship to the real world. And so the gaps going forward are basic science. What are the conditions? Well, we know what the conditions are going to be. How is our rocks going to behave in those conditions? We need to understand and modify our reservoir modeling techniques to really reflect the natural conditions. We haven't had a chance to really validate any of these models because we haven't got down to these conditions yet. But one of the things that's holding us back in that regard is high temperature tools. And so we are working with some providers. We're reaching out to most people saying, we need high temperature tools. We need tools that will hold up at these conditions. Even anything above, most tools fail at 180 degrees Celsius. We need tools that will hold up to 250 degrees Celsius. We can cool down to 200, 300, 200 degrees Celsius, but we need the tools that will hold up at those conditions. And so we're close. It's an engineering problem, but we're waiting for it to be overcome. And so we've identified the technology gaps. We've made a couple of publications out there identifying different materials and where we need research and where we need improvement in the SuperHot Rock regime. Drilling well completions is one. So directional drilling, zonal isolation tools. We need better reservoir creation and management. We need high temperature materials. We don't have any proppants that work at these conditions. So if we're going to be doing tensile failure stimulation, we need something to hold these fractures up. We need diverters to control fluid flows at these conditions. We need tracers at these conditions. Most tracers break down at about 200 to 300 degrees Celsius. We don't have any power plant designs at these conditions. So power plant designs really, they either top out at about 250 degrees C for traditional hydrothermal projects, or they're optimized for 800 to 1100 degrees C. So that's coal plants, nuclear plants, natural gas plants. So we're sort of in a shoulder regime here in the SuperHot Rock realm. We're going to be producing waters between 350 to 450 degrees C. We need power plants that will optimize for that. We don't have those yet. We have some ideas, but we don't have anything on the ground. So we need better modeling to understand we need to verify the models that we have. We need to improve the models we have based on field data. We need better resource characterization tools. So better seismic monitoring tools. There's a lot of work that's been done in the last 5 years looking at nodal arrays at the surface, DAS, electromagnetic induced tomography. There's an interesting technique looking at naturally occurring fluctuations in the electromagnetic field induced by fluid flow. We need to understand, and this is where my training comes in, is looking at how fluids will mature over time. I'm a geochemist by training, and this is really something I think that gets neglected a lot when people are looking at trying to develop SuperHot rock reservoirs. Is if you put water down into these conditions, how is that water going to change kinetically? We know ultimately the equilibrium chemistry point. We can look at naturally occurring supercritical systems and see what these fluids will become over time, but we don't really know how quickly those fluids will evolve. We don't know how those fluids are going to react with the rock in the near term, in a period of hours to weeks, and we don't know how those fluids are going to behave when they encounter different metals, different casing materials, different surface materials. So a lot of work has got to go into fluid and materials interaction. So we have a couple of papers looking at these data gaps. These are getting a little dated. They're a couple of years. We've done some more work looking at data gaps and how technologies can be advanced. And so the Mazama program has identified several different technologies that we're going to be carrying forward that we think are important. One of which is directional drilling. So directional drilling occurs, the oil and gas has figured out how to directionally drill, but their tools don't work at these conditions. They just flat out don't work. We've made some progress trying to marry high temperature electronics organizations with directional tool providers. We're making some progress on looking at where the shortcomings are. A lot of it's in the electronics and getting monitoring while drilling and logging while drilling tools to operate at these conditions. So we've made some progress, some very preliminary progress on how to update these tools and make them affordable. Right now, if you want to directionally drill, we can do it, but it's expensive. You got to use things like bent subs. It's a lot of trip time. It's a lot of pre-planning in order not to have breakdowns and cooling and unwanted downtime. We want to get up to the point where we want kind of the directional drilling efficiencies that the current oil and gas providers provide and that they enjoy. If we can do that, we can greatly enhance the economics of these programs. Being able to directionally drill is going to be important in order to encounter the naturally occurring stress regime and getting our fractures. We want to get the well oriented right so we can get our fractures right. And we can maximize our fracture implementation. The fracture direction will increase the economics of the reservoir. We need better tools. So the picture on the right is a borehole televiewer diagram taken from the Newberry 5529 well. This kind of work is key for planning your well and planning out your well direction, and being able to gather this kind of data at these kind of conditions is absolutely vital. Right now, the maximum temperature that the borehole televiewer tools go are 280 degrees C, and that's only one tool that I know of. It's owned by Sandia. It maxes out at 280 C, so we can cool down to the conditions that'll get us there. But this is a one-off tool. We'd like to have more of these and have them be a little more robust. This tool is, if it overheats and it fries, then we've cooked it, and there's no longer we can't use it anymore. We can't plan our new wells, and getting your well in the right direction is absolutely vital to making a successful program. We need some better well completions. The stresses that are induced by the thermal cycling in these high temperature wells is pretty daunting. There's just the loads are in hundreds of thousands of pounds. The ISOR group out of Iceland has developed, as an example of a tool that will work or can help work things along. They've developed a flexible coupling that provides for expansion of the casing at high temperatures. These haven't been proved very well in the field. I think they've got one in the field so far. The price point has made them really sort of unattractive to putting more of these in the ground, but they're designed to expand. They do leak, so you have to cement around them. they need to be optimized, but these are the kinds of tools that will help our well casing design and help make our wells more flexible. It's not optimum to cement everything in. It really sort of reduces, while it locks in your stresses and reduces your failure, it also locks in your flexibility. So your ability to use wells for different types of scenarios, whether it's injection or production, controlling your flow, using things like sliding sleeves. You lose that when you cement everything in place. Titanium couplings are great, but they're tremendously expensive. We're trying to work our way around that. We can design so we don't have to use the super expensive materials, gives us more flexibility and the ability to put more wells in the ground. So, of course, the more expensive a well is, the fewer wells you can put in. The fewer wells you put in, the less learning you take from the field. We're working on more rock fracture mechanics in the lab, looking at how rocks fail at these different conditions. This graph in the lower left is an example of rock strength as a function of temperature. So you can see this is differential stress. This is failure as a function of differential stress. That this is moving from 600 degrees C to 950 degrees C. This is some work done out of Switzerland at the EPFL lab, Marie Volet's work. They do a lot of really good work in Marie Volet's lab. I'm giving her a plug because we've supported some of that work and we've learned a tremendous amount about how rocks fail at these brittle ductile across the brittle ductile transition zone. We've looked at two rock types just preliminarily: basalts and granites. So microcrystalline, but microcrystalline mafic rocks versus macrocrystalline felsic rocks. Their behavior is quite different. We want to look at a lot of other different rock types and see how they fail at different conditions, the different pressures and temperatures in the SuperHot Rock regime. There's a lot of other different rock types we can look at. One shortcoming right now in the current worldwide availability of laboratory facilities is that there isn't a lab out there that can handle a rock sample that's more than about 2 inches in length and by 1 inch in diameter. So we're limited in a rock scale, and that really limits the scale of phenomena we can look at. So while we can look at the induction, these are all induced fractures created by failure by thermal shock. These rock samples aren't big enough to have any naturally occurring features in them. So like fractures or striation or myelination within the rock samples. So we would really love to see someone develop a lab that can handle the macro scale samples, the large scale samples. It's expensive. These labs can be dangerous because they have a lot of contained energy. Compressing a rock to 200 megapascals at 450 degrees C, it's essentially a bomb. So a lot of labs are very reticent to build these facilities. We've learned a lot from the smaller scale facilities. We're hoping that we can scale up and build larger labs and teach us a lot, because that does save us a lot of work and time and energy going underground. Now, this is an example of how we can learn a lot from off-the-shelf technology. This is a flow reactor. The GNS facility in New Zealand has several flow reactors and has demonstrated how doing bench scale experiments at supercritical conditions, looking at how waters evolve chemically with different materials, we can learn this kind of work. There's a lot of white space. There hasn't been a lot of work done, but these kinds of materials exist out there where we can do this stuff at bench scale. So this is looking at how waters evolve in a supercritical reservoir in contact with different materials. This reactor, for example, can get to 5,000 psi and over 500 degrees Celsius. So just packing this up and running different solutions through it in the short term can tell us a tremendous amount of information about and de-risk a lot about what we're going to be doing in the subsurface. So we're going to be doing more of this here in the United States, and it'll teach us a lot about what we can do and what we can't do going forward. And we're looking at different technologies for reservoir stimulations, looking at different materials that can help us in the subsurface, different types of cement, different types of sealants, external casing packers. I know that the WellTech group out of the United States has developed some really interesting external casing packers that are I think they're rated up to 350 to 400 degrees C now. These are great new tools with a lot of promise for being able to achieve the kind of stimulation goals that we're after. And then I want to talk about materials a little bit more. Proppants. Proppants are really sort of one of the Achilles heel for this kind of approach to doing geothermal reservoir development. And that is, how do we keep our fractures open? Traditional proppants all dissolve. or at least quartz sands will dissolve at 300 degrees C. They just, the kinetics are such that quartz just doesn't want to hang around. Ceramics don't want to hang around, they dissolve. Bauxite doesn't want to hang around, it dissolves. Materials that will hold up tend to be too dense, they tend to be too brittle, and so they don't hold up as a good proppant from a physical perspective. So we've got chemical incompatibilities, we've got physical incompatibilities with existing proppants. We really need to spend some time looking at different materials out there. There are, the material science research on this stuff is tremendous. There are hundreds of thousands of different types of materials we can look at, and we need to marry sort of the material science group, people who are outside of the oil and gas regime doing stuff in different technology, different fields, and bring them into oil and gas, bring them into geothermal, and talk to them about what they've learned, what they have. There's a lot of materials sitting on the shelves that were designed for other uses that we don't even know about, that are sitting there unused, unthought about. And I can't tell you the number of times I've talked to folks who are retired, who are emeritus status, who worked on these things 20 years ago, and we're working on trying to recover their notes and bring a lot of these materials back into use, back into understanding. I don't want to reinvent the wheel if someone's already developed materials that are out there. So paths forward, demonstration projects are key. We've done, I wouldn't say a lot of lab work, we haven't done a lot of modeling, but we've done enough at this point that getting into the field and de-risking technologies in the field is key. We're at that point now. The Department of Energy, the U.S. Department of Energy has put out this, they're going to be funding at least 4 demonstration projects this year or early next year, 4 different EGS demonstration projects. One of those is a super high temperature project. We put our proposal in. We hope we're going to be a leading candidate. We hope that'll be us. If not, we will probably apply again. It is a rolling process, and so the Department of Energy is now really pursuing demonstration projects. They have an office of demonstration projects now. They really see the benefit of doing demonstration projects in the field. It's time to get out of the lab and make this stuff happen. These are the demonstration projects that exist in SuperHot Rock space currently. All of these projects are either dormant or near dormant state. So some of the work has been done now, but we're really sort of just scratching the surface on what's available. So the SuperHot Rock realm, we're just getting started. In conclusion, one of the things I got to stress is when our company, when we go forward to the oil and gas engineers, they all sort of balk at the temperatures we're looking at, but these temperatures aren't that hot. This is, if you've got a pizza oven, this is the kind of temperatures you're looking at. And this is what I've got, a pizza oven in my backyard, and it gets up to 750 degrees Fahrenheit. It gets up to 400 degrees C. We can handle these conditions. We've certainly at the surface, the nuclear industry, the oil industry, the gas industry, the coal industry has all demonstrated how to handle these fluids. It's just getting them to the surface. And the Newberry volcano, we think, is an optimum location to do it. We think that those conditions are shallow enough that we can drill into it. We don't have to rely on new drilling technologies to get down to those conditions. We think it's going to be a premium location. That is the last of my slides, and I will take any questions.
Thank you very much, Jeff. Really appreciate it. A very interesting presentation. I thought the end was it's pretty funny about the pizza oven moment. I guess the oil and gas professionals, we should not fear temperature that much. So we got a bunch of questions in the chat. I'm going to start off with the first one that's already been answered by you. So we'll move on to the second one from Jovan, and he says, from your point of view, which are the main areas where we still need technology and material improvement to achieve those depths on well and system construction looking on subsurface? I think you've
material improvement, I would say it's a tricky question. One of which, I mean, my personal bias is towards compatibility, so material compatibility with supercritical fluids at depth and as temperatures come up well. So that's important. I would say cementing technologies that's a material science that it is being improved, but needs more improvement. There's several different cements now, new cements that have just come out in the last couple of years that need to be proven. And it sort of, I would say experience working with these materials is important. There's a lot of lab work that has gone into developing new materials for high temperatures. There isn't a lot of experience working with these conditions. So I would say that's really important.
All right, thank you. If you don't mind, do you want to stop sharing the screen? That way they, we can see. Thank you. So the next question says, from Keita says, has a closed loop of 80 kilometers well been drilled, or is it just a concept?
That's just a concept. I would say the most closed loop that's been drilled is the Ever loops. I think that I'm not sure the maximum amount of drilling they have achieved, but to get that's the 80 kilometer. That's sort of that's really a hypothetical condition. That's a math. It's a calculation done to try to match the amount of surface area that we're talking about. So to get the kind of surface area that an enhanced geothermal system in a SuperHot Rock reservoir can achieve, you need that much drilling in a closed loop system. It's not really practicable.
Yeah, that was for the comparison purposes on that slide. And then he followed up with a question, which I think maybe you touched a little bit upon, which says, is any zonal isolation used for EGS? If yes, what kind?
Well, so let's see. The best zonal isolation tools right now, I think, are we have thermal degradable materials. That's what we've used at Alterock and at Mazama. These are materials that break down at temperature, so you can temporarily isolate high flow zones with these materials that will either flow back or thermally degrade. They haven't been tested at these higher temperatures yet, so we don't know exactly how they'll behave. That's one of the reasons for our flow reactor work, is to see how our zonal isolation materials will work. There is some zonal isolation tools that are being developed. Sliding sleeve tools are being developed by several different providers here in North America. So there are some that are rated. They haven't been proved in the field. So we're really on the cusp of having zonal isolation tools. What's really, what's been used a lot in oil and gas are elastomers, soluble elastomers for zonal isolation, and they just don't work. You get above 300 degrees C and they basically blow apart, or they jam, or they don't come out of the hole at all. And they tend to, I know the Forge project tried to use an elastomer tool at 200 degrees C that completely had to be pulled out, manually pulled out. It almost ruined a lot of the casing. It didn't work at all.
So that area of isolation is actually very, very important because, and correct me if I'm wrong, I've heard in the past where, one of the conclusions was always try to stay away from open holes and having basically zero control of fluid flow, right? So being able to isolate zones and actually finding actual solutions for that is, I would say, at least in my perspective, one of the big ones to tackle at this point for this kind of development, right?
Yeah, flow control is absolutely key. I think sliding sleeves, personally, I think sliding sleeves are a very attractive option. And it would seem to me that that's probably the easiest tool to make compatible with these conditions, because you can make them, if you can make them with, all metal seals, I think they give you the most flexibility. It's just, I know they've been designed, I know they've been built in the lab. It's just, these wells tend to be so expensive, especially compared to oil and gas wells, that you don't get a lot of chances to test the stuff. You don't get to do a dozen wells and learn by doing. You've really got to take a risk and do it once.
One shot. All right. Well, I think the next question coming from Chelle, I hope I didn't mispronounce it. It says, regarding the stim operation, I suppose it talks about the Alterock work that was done. Did you stimulate open hole or cemented perforated with cased hole?
At Newberry, we did stimulation through open hole, and then we did it through perforated casing. We didn't do any stimulation through cement. Our temperatures at the time, so the cementing there only goes down to about 200 degrees or maybe 225 C. So the bottom kilometer of the hole, the bottom 1,000 feet of the hole is open. We did a stimulation program in 2012, and then we returned in 2014 where we put a slotted liner in because we had some sloughing, and so we wanted to keep the hole open. Going forward, we think that probably doing stimulation through a cemented perforated casing is probably the best way to get the best shaped fractures and gives you the best fracture control. You don't want to have, you can't do that in a production well. You want your production well to be as open as possible, of course, in order to interact with as many fractures as possible. So we can't. I know the Fervo group, they did do plug and perf in both of their wells, both their injection well and their production well. They didn't encounter as many fractures as they had hoped in their production well, but they are getting flow. It is working.
Yeah, and I think a lot of it also has to do with being able to have an optimal fluid distribution, right, from injector to producer, trying to avoid any kind of thermal short circuiting. And so designing the completion in the producer would take also quite some thinking, right?
Yeah.
Okay, I think you've answered the next question from Jella, so we'll jump on to Kalian's question. It says, is there a way to recreate, I think you've also touched on that, is there a way to recreate SHR conditions of rock samples in the lab for validating the rock behaviors from numerical studies? If yes, is any group already trying to achieve it?
There has been, it's hard because it's, no, I mean, well, we can do it on a small scale. Like I said, right now, the biggest samples, and I guess there is a comment in there that the Japan group, Watanabe's group, does have a larger scale lab, but it's still, they're still small. And it's a little bit, there is some question of the scalability of some of those results. And I think that's going to be proven through demonstration projects, is how well the findings in those labs scale up.
Mm-hmm. Okay, thank you. Yeah, there was a comment about from Keita on the lab. So Kalian also asked, due to the very high temperatures of SuperHot, how helpful do you think the thermal cracking stimulation is in addition to the shear stimulation when we inject the cold water?
I think it's very important. And one of the things we learned at Newberry was it's better to get away from the wellbore as much as possible in the beginning, so that you don't get too much fracturing in the near field. You want that fracturing, that thermal fracturing, to occur in the far field. So one of the things we're looking at is how to do fracture initiation, how to get fractures to initiate a little farther away from the wellbore to get away from the nil wellbore field stresses. So the thermal cracking is absolutely vital. Not only is it vital to creating the fractures, it's going to be vital for increasing the fractures, so increasing permeability over time. So you'll get some of the work we've done, is modeling work we've done, demonstrates that these fractures, and Mark McClure just has a paper on it recently, looking at how EGS can sort of self-perpetuate the fracture development over time. That those fractures will grow, and not only thermally, but they'll also grow chemically. We'll have more dissolution from the rock surfaces. That should happen. And if you can control your chemistry at the surface and keep your re-injected fluids undersaturated with respect to the different minerals, you can really increase your permeability in your field.
Makes sense. Thank you. And we have one more question from Kalian saying, what is your opinion on the economic performance of closed loop systems for electricity production?
I think it's tough. I don't want to, a lot of work is going into closed loop systems, and there's a lot of, I see the benefits and the attractiveness of it. When I look at how rock behaves, rock is an insulator. It's not a thermal conductor, and closed loop systems are all dependent upon conductive heating. So you've got to have a lot more drilling to get enough heat into your system to make it economic. So to me, more drilling is more risk. I know a lot of folks in the closed loop system like to take, they see more rock as more risk. They see the geothermal, the geologic environment as risky. There's a lot of unknowns. Anytime you go underground, things are unknown. But drilling is risky too, and it's expensive because more drilling means more casing and more cementing. I know that there is work going into trying to do caseless drilling. Different types of casing technologies are being worked on to try to reduce that cost. I mean, even if drilling was free, it would be tough to make geothermal economic at 200 degrees C. So the more drilling you do, the more expensive it gets. And not even so much from the drilling, but from the casing perspective and the cementing perspective. Cementing and casing are typically at least half of the cost of your well.
So we're going to need a lot more innovation in that field, because we talked about this, I guess, last week about economics and and how much we need to work on that, to enhance the projects. I think there was one comment from a question from Jella that says, are you expecting these wells to have scaling issues in production mode?
Tough question. That comes up a lot because one of the first questions is the chemistry is different for super hot rock systems and for supercritical systems. We feel that that's one of the advantages of doing it from an EGS perspective is that you can control the chemistry. You're starting with fresh water. If you can manage the chemistry at the surface, and there's that is a pretty mature industry managing geothermal fluid chemistries at the surface. So knockout boxes, taking out silica, controlling your carbonates. If you can control those at the surface, you can control those in the subsurface. We do expect there to be scaling issues. We do expect it's something you're going to have to manage and be aware of. A lot of our work going into our flow reactor, our lab work is going to be focused around that and managing that scaling. I don't think it's going to be any worse than traditional geothermal. I mean, geothermal projects have been dealing with scale for decades. If you look at the Salton Sea projects, I mean, it's a tremendous problem there because they have gigantic salt loads. But they manage it and they're economic and it works. So we're not reinventing the wheel here. It's going to be different, but we can figure that out ahead of time.
Thank you, Jeff. We had a comment in the group as well about well integrity and how much of a role that plays, and from all those failures, also some of those that you mentioned, and what can we learn from those points as well. We don't have any more questions in the chat. I would like to launch a poll real quick. Let me know if you see it on your screens. I believe you should be seeing it now. If you don't mind, just see what the choices are. So essentially the question is that, global geothermal power generation capacity stood at the year end of 2022, as per Think Geoenergy's article. And the idea is like how much, what is the megawatt that was at the end of 2022? We're having answers coming in right now. I'm gonna end the poll and I'm gonna show you the results. And if you see it right now, as we have 50% of the audience saying 10,832. And we have 33% that actually got it right, 16,127. I thought this was interesting to bring up because, doing a little reading, and you see in 2010, I think we had about 7,900 megawatt. And so in 13 years, we've come up to this number. That's more than 100%, about 100% increase. And I think part of your talk, Jeff, is, you were saying earlier when you mentioned the pizza oven, right? We need to understand that there's been challenges in the history, and we've managed. The energy world has managed to handle it. And I think it's super important to keep this perspective in mind, is with time, how things are changing fast, and for us to talk more, because the people that are in this call, of which a good part I know, are involved in several kind of projects, different kind of projects. And I do think we need to talk more. And I hope that this resonates with the audience and with you, Jeff, as well. I don't know what your thoughts are in terms of engagement and actually exchanging ideas, but I did get that from your presentation, that it is really crucial in terms of, I guess, doing better in the future projects, right?
Yeah, I mean, the answers are out there already. I think every question that we have, every technical roadblock we have in expanding these resources, getting to high temperatures, somebody's invented it somewhere. We've been to the surface of Venus. We know how to get there. It's sitting on a shelf. Whatever we're looking for, it's sitting on a shelf somewhere, I'm convinced.
Like that. Awesome. Thank you so much. Well, we don't have any more questions in the chat. I would like to thank you personally for taking the time, Jeff, for this really interesting talk. I'd like to thank the audience. We will be sharing the recording as per Jeff's agreement to the registered participants, so you guys can always go back and maybe share it even with your colleagues. Stay tuned. We're in for our last event in December 2023, and then we'll be coming back in 2024 with a whole new season of the special talk. So thank you very much, everyone, and enjoy your day and evening.
Thanks, Gabriel.